the outline of this research. And first, whenever you want to do some research, and you need to tell people why you do this research, right? Why you do this research, what kind of scientific gaps and you want to fill, and who will benefit this research, who might be benefiting from your research. So this is very, very important. Otherwise, the research will be useless. Nobody is interested. Nobody will benefit. So will be useless. So then we talk about 2D CEL FEM model. 2D we know that, and CEL is a coupled Euler and Lagrangian this model. So FEM model. This is abacus. Abacus we have, and I know I give you 2 assignments and for the FEM abacus model. You know and how to use abacus already. And then whenever we do this model, do research, and we need to validate our model. And so because numerical simulation sometimes is kind of interesting, right? Because there are a lot of parameters. And the first we need to do the convergence test to make sure our model is mesh dependent. So this is called convergence test. And second one is that, and you need to validate your model. And how to validate your model? And you need to compare your simulation results and against the experimental result, right? Experiments is what we see, and what we see in the experiments is always true as long as you measure when you measure this is a component, measure this is the signals, and you measure correctly. So we need to validate our model by comparing the simulation results against this experimental results. So this is for validation. After we validate our model, we will call this model is validated model. So this validated model will be used for predictive modeling. Right? For predictive modeling means that for some actual experimental conditions, it is totally not feasible. But because I have already validated my FEM model, if I just change some parameters, I can do the prediction and for some conditions that experimentally are not feasible. So this is, and you need to know. I want my students to know. Then give the conclusion. So here is a research motivation, and so you can see, okay. So fatigue like wear resistance and the corrosion resistance of the machine components. Whenever we have all these things in our daily life, all these tables, even though they are made of wood, but you can look at the surface, right? So the surface, the fatigue and wear resistance, corrosion resistance are very, very dependent upon this is the machining processes. So this can be significantly affected by altering the dislocation density and the grain size in the machine surface. And dislocation density, if we use the microscope, and you can see the dislocation density. This is a microstructure, especially for these metallic materials. And the grain size, how big the grain size is. And usually, the smaller the grain size, the harder the material is, or the stronger the material is. So it is of greater significance to investigate the effects of cutting tool geometry and cutting conditions on the dislocation density and the grain size distribution on the machine surface. So when we machine this material, and because usually in any kind of this machine, it's very traditional machining, and there's a lot of heat will be generated. And in this area, in the cutting area, they always have some heat affected zones. Heat affected zone means that because of the heat and some microstructure in that area have been changed, have been altered. Usually this alteration is bad. Okay, this alteration is bad. So we want to investigate and how the cutting tool geometry and the cutting conditions. That means for our case, it is the cutting speed, the depth of cut, and this is the feed rate, and how these three independent variables can change the dislocation density and grain size distribution. So some researchers have investigated microstructure alteration and thermal machining in recent years. So let me tell you again, dislocation density and grain size, and they are two very, very important characteristics for the microstructural characteristics of the material. So we in this research, and we use the CEL FEM. CEL means coupled Euler Lagrangian method. The FEM model based on the commercial FEM software abacus. So this FEM model has been used to investigate the effects of newly developed microgrooved cutting tools on the dislocation density and the grain size in orthogonal cutting, orthogonal machining of this aluminum, and the insightful conclusions have been obtained. So this one have been done before. But this research we are going to talk about and how we use this model and to model to simulate orthogonal high-speed cutting of the CPTI. CP means commercially pure, right? Commercially pure titanium alloy using newly developed microgrooved cutting tools. So this is a research motivation. And here I'm going to show you the model. So in this case, you can see, okay, in this case, the length of workpiece is a 10 millimeter, but we use this meter, okay, because meter is the standard unit, and we use the meter in our simulation because abacus itself does not have any units, and it is the responsibility of the researchers and to specify the units and make sure these units are consistent. And so a coupled Euler Lagrangian FEM model based on abacus explicit is developed. But by the way, the abacus you use for the bar problem. You still remember the bar problem, right? Use abacus to solve the bar. We have a complicated force at one end, another end is beads. You still remember? That is abacus standard. That is abacus standard. Also, the metal forming is also abacus standard. Abacus standard mainly is this is a static problem. You know what I mean? Do you know what the static problem is? The static problem means that at all this distance, the equilibrium is achieved. You understand? The status is static. The static problem means that the load applied is so low that each of these time steps, we just can assume that this equilibrium is achieved. Have you ever heard of quasi-static? Quasi, Q-U-A-S-I. The Q-U-A-S-I in English language, it means half. Is it right? Kind of. Quasi-static is also sometimes the speed the speed of applying loads is kind of high, and still is very low, but it's kind of high, but it's still we can, and for simplicity, we just say call it quasi-static. And that whenever you see static, it means that we assume for each of these instances that we apply the load and the equilibrium is achieved, right? Equilibrium, we have three equilibrium equations. And the dynamic, that is for the abacus standard. However, abacus explicit is used to solve the dynamic problem. Dynamic problem means that the load applied is such quicker that you cannot ignore the dynamic effect. You understand, right? Dynamic effect is that this acceleration and the mass of the points need to be taken care of. You understand? MA, right? M is the mass, A is acceleration. If the acceleration is high, MA is inertial force will be high enough that you cannot neglect. Make sense? So I mean, the abacus explicit is for dynamic problem. Look at this one. This machining. Machining is the speed is high. This is abacus. Abacus standard is for the static problem. Right? So for this one, we use abacus explicit. So the linearly interpolated, thermally coupled, is thermally coupled. So usually IBM is used to solve for the displacements. But for this we use these elements and they coupled. This is the displacement and the thermal. And so this is CPE for RT with reduced integration and automatic hourglass control are used in this CEL. So what is hourglass? Hourglass, automatic hourglass. This hourglass is the advanced concept. Hourglass means that in IBM, okay? In IBM, do you know hourglass? Do you know hourglass? To measure the stand, right? A glass, a device filled with stand. The stand is going down through the orifice. You can use that one to measure time, right? So hourglass here means that sometimes you will the problem cannot be solved. And so because the shape just like the hourglass. This is called hourglass control. So here you can see, okay, we have several regions. So we have four regions, 4 zones. This is and here, okay? So here is this is the problem domain, and here is the zone A. Here is the zone B. Zone B is this part. So here is the zone C, and the chip is zone D. So in this one, Euler and Lagrangian. Euler means that, let me tell you guys, Euler means that in this FEM formulation, the point does not move. Even if, that means the points, the material points, and the mesh, they are independent from each other. Okay? Euler. So however, Lagrangian means that the material points and the mesh, they are connected together. So as long as the material points are moving, the mesh will be moving. So that's the reason Euler is used, is very, very suitable to model is the water, is the fluids. I know these concepts are very, very high for you because you are so young. Okay, but I want to introduce this one to you. So in this case, we assume this material is moving like the fluid. That's the reason we use this is the Euler Lagrangian method. So this is the current speed. The material is feed from this entrance. We call this entrance, and we call this exit. Is the material flow. So here is the height of the workpiece. This is zone B, zone C, and zone D. And so here is the tool. You can see is the tool. So zone A is our area. The mesh constrained as entrance. The mesh constrained as the entrance. This is the zone A. And the zone B here is our area. The mesh constrained also. C here is a Lagrangian mesh constrained vertically. Mesh constrained, you cannot move in this vertical direction. And zone D, Euler area, mesh constrained vertically also. And this is a mesh zone D. So this is kind of advanced, okay, but I still want to introduce this one to you. So here is a mesh, the mesh for typical formulation and workpiece CPTI. So here at the very beginning, we call this one we just specify a feeder rate, okay, and a feeder rate. And here is a predefined initial the chip thickness here. This one, I'm sorry. This is F. This is a predefined initial chip thickness. So when this is the simulation reaches the steady state, so this is the chip thickness will be changing. So the friction coefficient between the tool and the workpiece is 0.4. So this one is obtained based on the experimental forces measured in machining. So if we want to model some physical process as close as possible, and all these boundary conditions, all these forces, loads must be as close as the reality. So here is the mesh model. This is the mesh. Any questions for this slide? I know this is advanced for you, but I want to introduce this advanced concept for you. And then we talk about this is the parameter, because we are going to use this density to model this evolution of distribution density. So here is a distribution density based model. This is the material parameters, and they are given from this is reference number 1. Right? So here is the mechanical and physical property of these CPTI, commercially pure titanium alloys. So this is Young's modulus, Poisson ratio, density, and heat capacity, thermal conductivity, along with the thermal expansion coefficients. And they are given here. This is from this is a reference 1 and reference 23. So here is heat capacity is temperature dependent, and so you need to enter all these things, because in the machining the temperature is changing. So these are the heat capacity and thermal conductivity, and these they need to be entered also. So not just use the constant these values. And then we use the Johnson-Cook model and to describe the material behavior for this CPTI. So this is Johnson-Cook model, right? And so this is the ABC, all this is the parameters for the Johnson-Cook model. After this one, I'm going to show you the paper and tell you something about the mathematics expression. Here, look at this tool. So this is we use a cemented carbide tool. So this carbide tool, the material parameters are given also: Young's modulus, Poisson ratio, density, heat capacity, thermal conductivity, along with the thermal expansion, and they are given here. And then cutting conditions. The cutting conditions where is also given cutting speed. This is the cutting speed. So you can see this 0.6. This is, you can see it is unit is meter. Okay, it's very high. It's a meter because the unit here I use a meter. The feeder rate, the initial feeder rate, we use this one. The depth card we use 1. The rate angle we fix the rate angle using 6 degree. Clearance angle 8 degree. The edge radius, how sharp the edge is, and we use 5 micrometer. So here, so this is a tool. This is a micro groove tool. You can see originally. So this is my original tool, the regular tool, but I just change. I just get some micro grooves. I use it later, right? So this is what is the effect of these micro grooves? It turns out that because when the chip moves along, this is a rigor phase. So these micro grooves will reduce the friction. We will reduce the friction, the energy consumption, and also cutting forces will be reduced substantially. So that is the significance of using micro groove cutting tools. And so here is the pattern of this is micro grooves are changed. So edge radius, so this edge radius, and we use 20. The groove width is from here to here, and WI we use 3 values. Okay, so we use multiple tools. But for this one, we change 20, 28, 40, 100. And the convex tool width from here to here. This is DI, and we also use 20, 50, 100, and the macro depths, how deep the macro grooves are, and we use 5 micrometers. So this is macro groove cutting tools. So here, this is a schematic illustration of material model. So first, the starting simulation, then initializing the material parameters. We need to get this data. And then we use S field. This is subroutine. And Abacus does not have this one. You need to write this subroutine and using this Fortran language, and then link. This is a subroutine with the Abacus. Okay? Use this one to be called subroutine, something like function you use in the MATLAB to compute grid size and dislocation density, and then updating GS and DD dislocation density, and calling subroutine view hard to compute the flow stress. So this means the Johnson-Kruger model, and then update DS, GS, temperature, and stress and strain. Then you check whether it is completed or not. If yes, stop. Otherwise, and go to another time step, increase the time. We will have one time step. So here is the results. So here is the dislocation density. You can see dislocation density as PV 15. Because dislocation density is a variable that Abacus does not have in itself. That's the reason we use this is a VUS field. These are user-defined variables. And to denote, we want to capture this STV 15. So here is by CEL model developed in this research. This is what we have here. So this one is dislocation density distribution predicted by reference number 1. And we compare the error for the maximum value is 0.2%, and the error for the minimum value is 0.2%. So whenever you want to validate your model, and you can either do the experiments by yourself, and then compare your simulation results with your experimental results, and to see to validate your model. Another way is that you compare your simulation results with the experimental results or numerical results that are available in the literature. Right? If their results have been published, that means they have been verified. Supposedly, especially for these very high-level journals. And then we talk about this free size distribution. This is using our research. So this one is also from the reference number 1. The error of maximum value is very small, 0.1, 1.0 percentage is very small. The error of minimum value is 0.3 minimum, 0.3 percentage. So here, temperature distribution, validation. So see, the temperature distribution is 0.6%. Minimum value is the same. A distribution. And then here, we validate our validation. But here, this microgroup tool. So you can see this is a physical photo. You can see it. You see, right? So here, this is a tool. You have used the tool insert, right, for the turning. So this is the grooves. And these grooves, we use the laser and to get these grooves physically. And this use a burn, laser ablation, and to burn, and this is a carbide tool to get these grooves. And then we do experiments. Right? So here, and we do the simulation, and we have the tool, and the Dolly has done experiments using this microgroup tool, and they have experimental FC. FC means the cutting force. LT means the thrust force. And then we compare the cutting force between experimental results and the simulation for regular tool. Regular tool means that the tool before we get these microgrooves. And the microgroove tool and the cutting speed of 120 meters per minute. So this is a groove tool. So this is a regular tool. Regular tool means that this tool does not have any microgrooves. I'm going to compare. So here is a simulation. Here's experimental, simulation, experimental, simulation, experimental, simulation, experimental. So you can see it's very, very close. That means our model is great. And we also validate the temperature distribution. And we have not done the temperature distribution measurement by ourselves, but we compare our temperature distribution against the literature, against the result that is available in the reference 24, in literature. So this is very, very close. And so this is when we compare these two, the distribution here, and also here this is the legend. So this is very, very good. That means we have validated our result. And then we look at how the width of this is a microgroove affects the chip thickness, right? Affect the chip thickness. And so this is a regular tool. So this is tool that have microgroove of width 20 micron. So this is width of 40 micron. This is width of 100 micron. We found that here the chip thickness, okay, chip thickness, the width 20, we have the lowest chip thickness. So another tool is this is the effect of the width on these cutting forces. So here's FC is cutting force, FT is the thrust force. The cutting force is in the cutting direction, thrust force in the vertical, perpendicular direction to the cutting direction. So you can see it's changing, it varies as this is microgroove width increases. As you can see here is lower, FC is low. Here's FC is also low. Then we can look at the grain size. The predicted distribution of grain size along the depths, from machine surface for various going down, for various microgroove widths. So there are four the curves. This curve is regular tool, and so this is radius 20, width 20, convex is 20. So this is a width is 40. So this is a width is 100. We have three curves. We can see for this one, right, the grain size, and so this curve is deviate from these three curves. And then we predict the dislocation density for this tool. This is one microgroove tool. So this is another microgroove tool, and this is the third microgroove tool. And we can see this is very, very close for these. For these three tools, and also for regular tool. So here, so this is a predicted distribution of grain size along the depths from the tool chip interface for various microgroove widths. So grain size, and this is the depths from the tool chip interface, the depths. So here, regular, and these are three tools here, is regular. So I'm sorry, this one is still this is the first microgroove tool here. And so this one is a predicted distribution of dislocation density along the depths from the tool chip interface for various microgroove widths. So this is the depths from the tool chip interface. Okay, this is the chip. So here is in the chip. These are depths from the machine surface. And so here is from the tool chip interface. You don't know the difference is? Here. From the depth, from the surface, machine surface, from here to here, go down. How the grain size changes and how the dislocation density changes. From the depth from the two-chip signaling, the two-chip interface is from here to here. Okay, everyone? Be careful. So because the chip is compressed, the grain, all these items in the chip, they have been compressed. So usually the grain size is changing a lot here. Be very careful, don't be confused. See the depth for machine surface is machine surface going down. Depth from tool chip interface is a chip, is a tool, from here to here. So this is a tool chip interface, is in a chip. So here is a dislocation density for regular tool, dislocation density. So this is predicted distribution of grain size for regular tool. The grain size is also another variable that we define, and it's SDV22. So this dislocation density is SDV15. Okay? Here is a microgroove tool. So this is a dislocation density distribution. So here is the grain size distribution for the same tool, 20, 20, 20. So this is edge distance, groove width, along with the convex width. All of them, all of these three values are 20 micrometers. So another one is 20, 40, and 20. So you can see, when you compare this one and the previous one, you will see the difference. So another, I have one question. Why this tool is represented using the green color? Because here the tool, we assume it is a rigid, okay? Rigid tool. It's a rigid tool. Let's see the distribution of these green size. So we use another tool, dislocation. This tool is different from previous one. It's shallow. And see the shallow. So this is the distribution of the grain size for this tool. With the groove width is 100. So chip thickness with microgroove convex as width. That means the difference between the one groove microgroove to another groove microgroove. And so we found that here, when the convex here is 20, the chip thickness is the lowest one. And also the cutting forces, FC, and this is the thrust force, FT. And it also have this kind of trend, the trend. Regular one is very high for FC, but you can see, so this is for these three cases, and the cutting force is reduced. For the thrust force, it's very, very interesting. Interestingly, these four guys, they are comparable with one another. So here is the depth from the machine surface, grain size. And for this is now this time we change the convex length. Right? So you can see here, and this one, this curve deviates from all other three curves. And so also, we are checking this is the effect of convex length. The depth from machine surface from here going down. Is a grain size. This is distribution density. This is grain size. I'm sorry. It is grain size, and this is from the tool depth from the tool chip interface, and this is the chip. Here is also depth from the tool chip interface. So some students might ask, why these three curves are so long, but this curve is short? The reason is that these three curves, right? 1, 2, 3, for these three cases, the chip thickness is comparable. And however, and for this one, the chip thickness is much lower. So this is from here. Here, this point is on the tool chip interface, and here is how long from here to here is how thick and your chip is, right? So here is a distribution of distribution density. So this is a distribution of the grain size. Also, this is the distribution density. And for another tool, one convex equals 100 micrometer. The same tool as this one, but this one is for the distribution of grain size. So conclusions. In this paper, Abacus is used to model orthogonal carding of CPTI to investigate the effects of microgroup carding tools on distribution density and grain size distribution in the machine process. So a coupled CEL FEM model based on Abacus is developed, and this model is able to capture the essential features of orthogonal carding of CPTI, and the CEL model has been validated by comparing the simulation results with the results available in literature. Right? Because we did not do the experiments by ourselves, and we use the experimental results that are available in literature as a reference for comparison. So in the machining of CPTI, the microgroup widths can effectively alter the grain size distribution and distribution density along the depths from the machine surface, right? Machine surface going down, and along the depths from the tool chip interface. That is from the tool chip interface and going inside, this is a chip. For this means this can affect grain size and distribution density in both this direction and that direction. So in this machining, the microgroup convex is convex. Widths can change grain size distribution and distribution density along the depths of this from the machine surface and also along the depths from the tool chip interface. The surface integrity of the machine surface might be altered based on needs if the appropriate microgroup widths and convex widths are selected. So you can do a lot of these combinations of this is the microgroup widths, the convex is the length, and also the depths of the microgroups. So this is pretty much the presentation I have. Any questions so far? No questions? I'm going to show you the original paper. So this is a presentation I gave, the PPT file. I want to share with you. So this paper, what I want to talk to you is about. This is the two models. These are two figures I presented already. So here is the distribution density based material model. You can see, okay? So this is a lot of mathematical details. I want you guys to take a look. This is not required, it's not mandatory, and I would suggest you take a look. And so here, you can see the engineering, as an engineering guy, and we will use a lot of mathematics, right? So without mathematics, and we can only float in the water, or we cannot dive to get the treasure. And this is, I was always say the mathematics is so important for engineering people. To know something about this is distributed density-based material model. So these are parameters we used, and these parameters have been given in my PPT file. Another one is, so here is this one, right? This is what I give you in the PPT file, and you just take a look at this one. This is too mathematically intensive, so I will not read it line by line. The workpiece, we use the Johnson-Cook model. The Johnson-Cook model, Johnson-Cook model is widely used in machining and to describe the material behavior. Why? Because in machining, the strain rate is very, very high. You know strain, right? And the strain rate means the time is taken care of also. Because when we machine it, the strain rate is very, very high. So we use this Johnson-Cook model in machining. The Johnson-Cook model have several versions. For the original version and for different material, so these parameters will be different. Definitely, you need to do the experiments and to get this correct these parameters for your Johnson-Cook model. So here is a tool I show you. And so here is more figures. You can take a look at these figures. Okay, everyone. So I posted this one online already, so you can take a look. I will post this PPT file online also, and you will have a better understanding.